AI Frontiers. The AI Awakening Series, Volume 4. The Birth of the Digital Brain. Part of the Thinking Library. Part 1. Building a Mind from Mathematics. A child learns by touching the world. A hand reaches toward a flame and quickly retreats. A voice is recognized. A face becomes familiar. A language slowly emerges from countless small experiences. Human intelligence is shaped by interaction. But what if there were no body? No childhood. No senses. No world to explore. Could intelligence still exist? This question sits at the heart of modern artificial intelligence. The remarkable systems that have captured the world's attention were not raised in families or classrooms. They did not walk, eat, sleep, or dream. Their entire existence began inside enormous data centers where millions of processors performed endless calculations. Their world was mathematics. Their experiences were patterns. Their memories were numbers. To many people, this sounds cold and mechanical. Yet hidden within those calculations is an extraordinary idea. Perhaps intelligence does not require flesh. Perhaps at its most fundamental level, intelligence is the ability to discover relationships, predict outcomes, and adapt through experience. Modern AI was built upon that possibility. Scientists did not try to recreate every detail of the human brain. They sought something more practical, a system capable of learning from examples. The challenge was immense. Programming every possible answer was impossible. The world contains too much complexity. Instead, researchers needed a machine that could teach itself. And so they turned to one of nature's greatest mysteries, the human brain. Not to copy it perfectly, but to borrow one simple principle. Learning happens through connections. Part 2. The idea of the artificial neuron. Inside the human brain are billions of neurons. Each one is remarkably simple. A neuron receives signals. It processes them. It passes information onward. Individually, a single neuron accomplishes very little. Together, billions of them produce language, imagination, memory, and thought. Early AI researchers wondered whether machines could use a similar structure. The answer was the artificial neuron. Unlike its biological counterpart, an artificial neuron is simply a mathematical function. It receives numbers. It performs calculations. It produces an output. One artificial neuron is not very impressive. Neither are 10, or even 100. But connect millions of them together, and surprising things begin to happen. Patterns emerge. Relationships are discovered. Predictions improve. The machine gradually becomes better at its task. This structure became known as a neural network. The name sometimes creates confusion. These systems are not miniature human brains. They do not contain emotions or awareness. The comparison is more like the relationship between a paper airplane and a bird. One inspired the other, but they remain fundamentally different. Still, the principle proved powerful. A network could begin with random connections. Then, through repeated exposure to data, those connections could strengthen or weaken. Mistakes would become less frequent. Accuracy would improve. The machine would learn. Not because someone programmed every answer, but because the network slowly adjusted itself through experience. It was a simple idea, and it would eventually change the world. Part 3. Learning through failure. Imagine teaching a child to throw a ball into a basket. The first attempt misses. The second comes closer. After hundreds of tries, accuracy improves. The child learns not because every movement was explained in advance, but because failure provided information. Artificial intelligence learns in much the same way. A neural network begins with almost no useful knowledge. It makes predictions. Most are wrong. The errors are measured. Tiny adjustments are made. The process repeats. Again, and again. Millions. Sometimes billions of times. This process is called training. For a language model, the challenge might be predicting the next word in a sentence. The sky is blue, cloudy, dark, bright. The system makes its guess. If it guesses incorrectly, the network adjusts itself slightly. Over countless repetitions, the predictions improve. The machine develops an increasingly sophisticated understanding of language patterns. The same principle applies to images. Show a system millions of photographs. Tell it which contain cats and which do not. Eventually, it discovers patterns that humans never explicitly described. Whiskers, ear shapes, eye placement, body proportions. The machine builds its own internal representation. Learning emerges from correction. This approach may seem inefficient. In some ways it is. Training advanced AI systems requires enormous amounts of computation. Yet nature itself appears to rely on a similar strategy. Humans are not born knowing how to speak, or read, or solve equations. We improve through repetition, feedback, and experience. Modern AI simply compresses that process into mathematics. Part 4. The hidden world inside the network. One of the strangest aspects of artificial intelligence is that researchers often cannot fully explain how a trained network reaches its conclusions. They understand the architecture. They understand the mathematics. They understand the training process. But inside the completed system, millions or billions of connections interact simultaneously. The result becomes difficult to interpret. An image enters. A prediction emerges. Somewhere within the network, countless calculations have transformed pixels into meaning. This hidden complexity has led some researchers to describe advanced AI as a black box. Not because it is magical, but because its internal reasoning can be extraordinarily difficult to trace. This creates both excitement and concern. The excitement comes from capability. The network often discovers solutions humans might never have considered. The concern comes from trust. If an AI recommends a medical diagnosis, approves a loan, or helps guide a vehicle, people naturally want to understand why. Transparency becomes important. Researchers around the world are now working to make AI systems more interpretable. They seek ways to peer inside the digital brain, to understand which patterns it notices, which information it values, which paths lead to its decisions. The effort resembles neuroscience itself. Scientists can observe the human brain. They can measure activity, yet many mysteries remain. In an unexpected way, humanity now faces two great frontiers at once: understanding biological intelligence and understanding the artificial intelligence we have created. Part 5. Why bigger often means smarter. One of the most surprising discoveries in AI research was that larger networks often developed abilities nobody specifically programmed. As researchers increased the number of artificial neurons, capabilities improved. The systems wrote better, reasoned better, translated languages more effectively, solved increasingly complex problems. At first, scientists assumed progress would be gradual. Instead, entirely new behaviors sometimes appeared unexpectedly. A model that could summarize text suddenly solved logical puzzles. A model trained primarily on language-generated computer code. Capabilities seemed to emerge naturally from scale. This phenomenon challenged existing assumptions. Perhaps intelligence itself grows through accumulation. A single neuron does very little. Billions working together create extraordinary complexity. The same principle appeared to hold for artificial networks. Larger models captured richer relationships. They built more detailed internal maps of the world represented in their data. This does not mean bigger always means better. Large systems require vast resources: energy, hardware, data, engineering expertise. But the pattern revealed an important truth. Intelligence may not depend on one magical breakthrough. It may emerge gradually as complexity reaches certain thresholds. Nature appears to work this way. And now perhaps so do machines. Part 6. The new kind of brain. Calling AI a digital brain can be misleading. It does not possess biological cells. It has no heartbeat, no senses, no inner voice. Yet the comparison remains useful because both brains and neural networks perform a similar function. They transform information into action. The human brain evolved through millions of years of natural selection. Artificial neural networks evolved through mathematics, engineering, and human design. One is biological. The other is computational. But both reveal something profound. Intelligence may be less about the material from which a system is built, and more about the relationships within that system. Connections, patterns, learning, adaptation. Perhaps these are the true building blocks of intelligence. This realization has begun reshaping science itself. Neuroscientists study AI to better understand the brain. AI researchers study the brain to improve machines. The two fields increasingly influence one another. The result is a fascinating partnership. By building artificial minds, humanity may gradually uncover the principles behind its own. And by understanding itself, it may create even more capable machines. The journey moves in both directions. Part 7. The Architecture of Tomorrow. Thousands of years ago, humanity built monuments from stone. Centuries later, it built engines from steel. Then it built computers from silicon. Now it is building something entirely new. Not structures, not vehicles, not simple machines, but systems that can learn. The digital brain is not alive. It does not dream. It does not wonder about its own existence. Yet it represents one of the boldest engineering achievements in human history. A machine that changes itself through experience. A machine that grows more capable through learning. A machine built not from muscle or bone, but from mathematics. Perhaps future generations will look back on this moment the way we look back on the first steam engines or the first airplanes. Primitive. Remarkable. The beginning of something much larger. For now, humanity stands at an extraordinary crossroads. We have not created a human mind. We have created a new kind of intelligence altogether. And somewhere between billions of artificial neurons and countless streams of data, the first outlines of a digital brain are taking shape, one calculation at a time.